Thank you very much for giving me the opportunity to talk here. I'm going to dim the light a little bit so you can see my slides actually. Most of them are a little dark. I think you can see this now. So, as you just mentioned, I'm going to talk a little bit about some of the research that we've been doing in our lab in the US and now in Berlin. And most of it will be focusing on trying to understand the spread of infectious diseases on networks. So, this image here later on will reappear, and then I'll explain to you what is shown. If I have time, at the end of the talk, I'm also going to tell you a little bit about our most recent research on trying to quantify the spread of Ebola on the worldwide air transportation network, and specifically trying to assess the import risks in various locations in the world. So this picture you're also going to see at the end. So what we do in my lab is we're trying to understand how emergent infectious diseases, most recently Ebola in West Africa, spread on the globe. A couple of years ago, in 2009, it was H1N1, and we're trying to make forecasts about this, try to understand these processes better, and I'll give you a little glimpse about how we try to do this in the next 45 minutes. So most of the things that we do is we deal with networks in epidemiology, and there are different types of networks. Some of the networks we'll hear about by Zero, they're essentially two different types of networks. So networks could be interaction networks or communication networks between individuals, where the individuals are the nodes, and their contact patterns, for instance, are the links in the network. But there are also other types of networks, like these mobility networks, where the nodes are locations somewhere, and the links quantify the amount of people that go between two locations. Okay, so keep that in mind. We'll be focusing on these types of networks. Essentially, what we do in network science, and I'm just pausing the presentation for a second to just illustrate this. As physicists, we look at these networks. This is one. We have nodes, and they're connected by links, and these nodes mean something, individuals or locations in space. And then there are essentially two questions that we ask. One is, what is the hidden structure in this network? For instance, if I take another network, let me try to find one. Here's my pointer. Let's look at this network, for instance. Yeah, this might be a network that we observe in nature, where we have nodes, and if we pull out a certain node here, for instance, this one, we can ask what is the structure. For instance, this node has a small connected community and a larger community. And so one aspect of network science is trying to look at these networks and extracting structure from them, from the mess of links and nodes. Another aspect of this is trying to understand dynamic processes on these networks. So for instance, if this is a network of places and the links is people traveling from A to B, we're trying to understand not only how these processes evolve, but how much of the structure of the network impacts on the dynamics that occurs on the network. So having said that, let me go back to the presentation and the next slide. Specifically, what we try to do mostly is, we look at mobility networks. For instance, this is the worldwide air transportation network, to which I'll come back in a second. And we try to understand how this network impacts global disease dynamics. This is a computer simulation of a hypothetical pandemic that starts in London. Okay? Now, why we do this is because we would like to ask specific epidemiological questions. One is, where is the epidemic going to go? When is it going to get there? How many people are going to be infected? And sometimes also, on what route do people travel or take the disease from A to B? And sometimes also, and I'll come back to this, there are situations where we have a spreading phenomenon. There are cases here and over here and there, and then we're trying to find the outbreak origin. Okay? So let me walk you through the way we look at these things. Okay? Let's start with a very simple example. It's an interesting color here. It should be blue. Anyway, so this is a simple spreading phenomenon that we often see in physics. There's a location where it all starts, and then there's a concentric spreading pattern. Okay, we see this when we throw a rock into the water. We see concentric waves. There are proliferation examples in physics, growth processes that all exhibit this kind of nicely geometric concentric disk if a spreading is happening in 2 dimensions. Now the reason I'm showing this here is because this is a pattern where let's assume this is some sort of idealized epidemic. And it starts here, and let's assume we're here, and we measure the speed of this, and we know the distance, then immediately we can just infer when the epidemic wavefront is going to reach us, right? You know, you don't have to be a mathematician to compute this. If you have the speed and you have the distance, you can compute the arrival time when we have a simple pattern like this one. And in fact, even in epidemiology, there are examples where this kind of pattern almost is observed. So an example that I always give at this, to illustrate this is the Black Death in the 14th century, which spread across the European continent as a wave, right? So 4 to 5 kilometers per day. Took a few years to cross this continent. In fact, there are people that use this kind of mathematics that describes this to understand these processes. So simple spreading patterns. And another video that I show in contrast to this is this one. Some of the people in the audience have seen this multiple times. It's actually a very old video clip of mine that I made like 10 years ago, I think. It's an illustration of the worldwide air transportation network, which just illustrates that nowadays we can go from point A to point B in a matter of days, and it also illustrates in what complex way we are connected. And of course that has an impact on how diseases spread. Let me just give you another illustration of how mobility works globally nowadays. This kind of network, global air transportation network, it's approximately 4,000 airports, approximately 25,000 connections between these airports, and about 3 billion passengers travel on it per year. And if you just look at the numbers, you can also compute how many kilometers all of humanity travels every day, and the result is 14 billion kilometers every day is what humanity travels. So just, it's just a number, but for comparison, to get a feeling for this is 3 times the radius of our solar system. So that is what humanity travels every day. So let me put this in contrast again. So here's again the sort of concentric pattern, nice concentric, and this is a computer simulation of the H1N1 pandemic and the global spread of this on the air transportation network. I'm sorry it's a little dark, but I hope even in the back you can see kind of the pattern. Now, what are the qualitative differences in these patterns? Now, be assured that the mathematics that generates this and the mathematics that generates this is structurally not very different. Structurally very similar, except for here, sort of mobility is only going to the next pixel in the system, and here it's happening on this network. And of course, immediately, and that is intuitively clear, there's an imprint of this network on the overall pattern. So I stopped it in the middle of the simulation here, and we see in comparison, if we want to make a qualitative comparison, here it's a nice geometry, everything looks very simple. He or she doesn't like my presentation so much. I'm sorry. It's probably because that pattern is so ugly. Anyway, what was I saying? Oh, yes. So now here we have a spatially, decoherent pattern, and unlike in this picture here, we cannot say, here we can say when is it going to get there. In this picture, we cannot do that so well. And this is the reason why, despite the fact that the mathematics of both of these is not so much different, we need computer simulations in which we plug in this and then run these simulations. But, the idea behind this, it goes back 10 years when we started doing this, was this assumption that essentially, the dynamics of the underlying process is not much different. All that we really need to know is the network structure, combine it with sort of conventional models for local disease dynamics, and then potentially make already some good predictions. And we started back then with SARS, and a few years later we refined models and then try to make predictions about this. For instance, this is a picture of H1N1 and a short time forecast we did with this idea of combining mobility networks with local dynamics for a disease and then trying to make some sort of forecast. And there's a whole industry about this, and the leading expert in the world is Alex Vespignani and Vittoria Kulica, who have developed this amazing platform called GLEAM, Global Epidemic and Mobility Tool. It's a client-server system. There's a whole team behind this, and it's a system where you can actually define your own pandemic, fix all the parameters, and then run a forecast. It's very, very awesome. So there are a bunch of teams that do this worldwide, but nevertheless, in all of what we do, there are some issues. And I'm going to focus on the issues today and how these issues that have been on my mind for some time made me think about this whole system in a very different way and how this then helped us understand it better. So the issues. What are the issues? Let's look at this again. Let's compare these two patterns again. Like I mentioned earlier, in this system, any child can tell you when I'm here, when is it going to get there. I just have to observe this pattern for some time, observe that there's a constant speed, and then I can predict when is it going to get to me. I don't have to write down any math for this, essentially. I can also, just by looking at the pattern, see that the origin of the spreading was probably somewhere in the middle, just using the geometry of everything. In this pattern, it's more difficult, right? So just by looking at this spreading pattern, it's very hard to say when is it going to get here or over here. And it's also difficult to assess where the origin of this pattern was, just by looking at it. Okay, and that's the underlying complexity of this network, and the reason, like I mentioned earlier, why we have to plug in everything into a computer and actually do computer simulations. Now that's all nice, but that's also an issue, because these computer simulations require fixing parameters of the system, right? So even though they work very well, when you need them most is in the beginning of a scenario, like the MERS coronavirus that started popping up here in Saudi Arabia, or the Ebola outbreak in West Africa. And I have to apologize, this is a bit of an old slide. There are only a few hundred cases, now there are a few thousand. So in these situations, when we need the models most and know the least about the infectious agents, the parameters, etc., that's an issue. We don't know so much, but we still want to run our computer simulations, but it's kind of arbitrary how we fix the parameters, etc. So when we need these models most, these computer models, they're least reliable. And there's another issue. Here I'm showing this slide. I always also show that to my students. This is two Nature articles. One is an article, one is a letter by the same guys who developed a very sophisticated agent-based computer simulation for the spread of pandemic influenza, hypothetical pandemic influenza at that time in Thailand and in the US. Now, when you look at these papers, they're 5 and 4 pages long, and you just read them and you do something very simple, also related to, word detection and text. If you just count the word assume in this paper and the word assume in this paper, you get 18 and 17. Now, from a physicist's point of view, this is pretty horrible, because every assumption here means fixing a parameter to a certain value. And if you know something about nonlinear dynamics or complex systems, then it means that if you have lots of assumptions, and this is a lot of assumptions in a 5-page paper, it becomes less and less predictable how robust your model is, because you can no longer systematically check what happens if I change this parameter a little bit. Okay, so that's also a disadvantage. And in fact, this sort of thing, this sort of reasoning, encouraged the former president of the Royal Society, Robert May, to publish a paper in Science, which is actually one of my favorite articles. It's called The Uses and Abuses of Mathematics in Biology. And I'm going to quote 3 things from this paper, which is, I recommend to everyone read it. He says in this paper, the increasing speed and sophistication and ease of use of computers enables an increasingly large number of life scientists who have no substantial background in mathematics to explore, in quotes, mathematical models and draw conclusions about them. And he continues and says, such activity usually consists of representing sensible and evidence-based assumptions as the starting point for a complicated and usually nonlinear dynamical system, assigning particular parameters, the assumed count, often in an arbitrary way, and then letting this complicated system rip. And then he says, we are seeing an increasingly large body of work in which sweeping conclusions, emergent phenomena, are drawn from the alleged working of a mathematical model without clear understanding of what is actually going on. I think this can be worrying. So in modeling, And specifically in sort of large-scale modeling enterprises, we're seeing the same kind of problem that also we're seeing in big data, where we have lots of data, lots of power in computers, and detecting correlations, for instance, and without a clear understanding of what is going on. So this sort of thing is also happening in modeling. Let me give you an example of this, yet another one. Coming back to to this year's Ebola outbreak. So this is the number of cases. This is also a bit of an old slide from like week 37 this year. This is the cumulative number of cases of Ebola, okay, up until week 37. And we can see like here, after we had like a few hundred cases, there's sort of a an exponential growth of the number of cases. And all of these dots are predictions of models. Let me go to the next slide and show you one that was, one such model was published in the New England Journal of Medicine, which is a sort of a high-profile journal. This paper right here, a very complicated system, has lots and lots of parameters, and at the end of the day, what it did is it produced this dot here, which is right on the line that I get when I just use my pencil and a ruler. Okay, so that's another drawback. We run these super complicated systems, and then at the end they produce an exponential growth. And another thing, and this kind of inspired me to look at it in a different way, is that when we did the H1N1 pandemic predictions in 2009, my friend and colleague Alex Vespignani and his team did also a model, and both, despite the fact that both models use different data, use different math, etc., produce very similar predictions. Okay, so different models produce the same kind of results. And finally, I want to mention this one, the Egg Outbreak in Germany. This was a foodborne disease where this problem was not only making a prediction, but really finding out the outbreak origin. You need kind of the initial condition to make a forecast. And in this case, it was like unclear for a very long time where this came from. Okay. So I started thinking about this as there's something more fundamental going on. How come there are like these different models? They make the same kind of predictions. Is it really necessary to run these big computer simulations, or is it possible that we just look at the system in the wrong way? And it turned out that something very simple actually helped, and that was this idea of redefining the notion of distance. When we look at these computer simulations on maps, what we really use is a traditional way of looking at things, using maps, the map of the world, for instance. And maybe that's no longer really an adequate way of looking at things. So let me show you what we did and explain it in a simple way first. Okay? Let's assume we look at this air transportation network, the global air transportation network, and let's pretend that we're here at this node, JFK, in New York. And we look at the number of people that move or like that travel from New York to London, or from London to Frankfurt, and from JFK to London, JFK to Frankfurt, and JFK to Pittsburgh and Raleigh-Durham. These places are close geographically, much closer than these two, but there's a lot more traffic going to these big hubs in Europe. So what if we just redraw the world from the perspective of JFK such that these places are closer, in a way that quantifies that if there's lots of traffic, places are closer. If there's little traffic, they're far apart. Super simple, right? And intuitive. The basic idea is places should be close if there's lots of traffic, and far apart if there's little traffic, okay? From the perspective of a given node. And there's a math behind this that defines this effective distance from a reference location, any node in the network. You pick a node, and then you define an effective distance to all the other nodes in the network. Okay? When you do this, and I'm going to spare you the mathematics behind this, and just give you this intuitive notion, you can ask, given you're here at JFK, what is the shortest route to any other node in the network? Short meaning effectively short, okay? So you place yourself on a node like this one, and then you ask what's the most effective route to this node, and you will probably make a few hops and go to this node. And what you then get is what is called a shortest path tree. Okay? And short meaning effectively, not geographically close. Now this still doesn't look very nice, but what we can do is we can pull out this tree out of the conventional geography and just redraw it in a different way. Okay? So this is done here. Here's again our reference point, JFK. And now this radial distance here is this effective distance that I mentioned here that takes into account that lots of traffic short, little traffic far away. And the little tree structure that you see here are the routes that you would take if you were to move along the shortest path to any destination. For instance, from JFK to whatever this node, you would go effectively across this node here. And you can see already, if you zoom in a little bit, that places like London Heathrow are closer to JFK than, for instance, Atlanta. There's Los Angeles, there's Frankfurt, Charles de Gaulle, Phoenix, Beijing. Okay, now you can do that. Look at the pictures and see if they make sense. And there's some intuition behind this. You can look at the world from a different viewpoint. In fact, you can do that from every node. This is Tegel in Berlin. Here you can see that almost everything else is reached through Frankfurt. Frankfurt is very close. Charles de Gaulle, London Heathrow. There's JFK a little further away. Las Vegas, Chicago, etc. And again, you can zoom in and investigate this, on a qualitative level a bit closer. And you can also do a sanity check and plug in the new airport in Berlin, and you'll find that everything is infinitely far away. Yeah, I made that joke once in Japan. No one laughed. So now, is that just a nice redrawing of the world? What's the big deal? How's it going to help me? The best way to understand this is by looking again at two computer simulations. This is a hypothetical dynamics starting in Atlanta. This is on a Greek island. Here's the conventional view, and it pauses here. And here is the view using effective distance. Okay? And remember that these pictures, these network representations, are derived only from the network, not from the disease dynamical model. It's just the network that we look at. And we see that what looks complicated here looks like a nice concentric spreading pattern in this new visualization. Okay? Which means that instead of using geographic distance or this sort of conventional representation, all I have to do is look at effective distance, and what seems complicated here turns into a simple concentric spreading pattern in effective distance. Now that's true really for every node that you can hypothetically start a pandemic. Here are a bunch of different starting locations. This is time, different snapshots. You can see the trees, they look a bit different in every picture, but on these trees, the spreading pattern is concentric. So the take-home message is, I'm going to show you two slides for comparison. Okay, here again is a network. Here's a snapshot of a hypothetical pandemic that started in Hong Kong. The red dots is where the pattern is very pronounced at a given point in time. And here is the arrival time of the epidemic as a function of geographic distance. And you can see there's a trend, and in fact, if you compute the slope of this, you get typical for influenza diseases like pandemic influenza, you get typical velocities of a few hundred kilometers a day. But what's important is not this trend. What's important is that if you fix a certain distance window, there's a huge scatter. So you can no longer, as was also clear from the videos I showed you earlier, you cannot use geographic distance as a predictor for arrival time. And that's true for H1N1 or SARS or any of the events that have happened. Now, if you just change this to the new picture, instead of the conventional representation, you use this effective representation. For the hypothetical sort of pandemic, everything collapses on a line. If you use geographic distance, effective distance, here on this axis, arrival time here, which means that if you know the slope of this, you can just use effective distance to predict the arrival time. And also on these real diseases, there's a stronger collapse on this linear axis. Now, I mentioned EHEC earlier, right? And this foodborne disease, where we had the problem of actually computing the outbreak origin. And in fact, there are a number of cases where something is spreading and we're trying to reconstruct where this came from. Especially like there are a bunch of papers that were published in recent years about sort of, cultural invasion processes, farming, how it was, invaded Europe, or how, people started migrating into the Americas. Where does this come from? So there are lots of scenarios where we have a sort of complicated spreading phenomenon. We're trying to find the origin. Now, the clue about this effective distance idea is that we saw that if we have a spreading phenomenon, look at it in the conventional way, it looks sort of spatially incoherent, and it's very hard to see the outbreak origin. When we look at it in the effective distance representation, everything looks concentric, but the clue is only from the reference point that is the outbreak location. Okay? Only from that location, everything looks nice and concentric. So we can use this actually to do outbreak reconstruction. So let's assume we have a spreading phenomenon at a given point in time. It looks like this, okay? Orange dots is where a disease is prevalent at the moment or has a high incidence pattern. And let's assume we have a bunch of sort of potential candidate outbreak locations, 12 of them here. Now I can look at this pattern from the perspective of all of these 12 candidates. All of them have a different effective distance representation, okay? And I just redraw this in these effective distance representations, and I will find that there's one of them for which the pattern looks most concentric, for which the circle is smallest and has the least amount of wiggle in it if you go around the radius, okay? And what is clear here in this qualitative comparison can be quantified. Okay, now I can look at a pattern. Do that on the next slide. Let's look at this one. These are 4 different time units. These are all the airports, and these are 2 quantities. Each one of them quantifies the size of a circle and the wiggle in the circle. How smooth it is as a circle. And I look at a spreading pattern at these 4 different times, and I record for every potential outbreak location how small the circle is and how regular the circle is. And the combined, small size and least wiggle in the or most regular circle is this one, and it's the outbreak location. So it's the closest one to the origin. It kind of separates from the cloud. So it's throughout the entire time. You can use the technique to, at least in principle, to identify outbreak locations. That works for the H1N1 or in other diseases where we applied it to. And specifically, it worked on the EHEC outbreak, where we didn't use air transportation, but food transportation in Germany. It identified the district, the county, where this actually came from. Unfortunately, we only had it after the outbreak occurred. So finally, as I promised you in the beginning, I'm going to tell you a little bit about what we did using these techniques for Ebola. How am I doing for time? I'm good? Good. Yeah? Excellent. So let me go back here and show you what we did for Ebola. Okay? So this is a very complicated figure. It's a website that you can go to, my group's website. So what is shown here? This is a reference point. It's one of the airports in West Africa, Conakry in Guinea. And what is shown here is this effective distance. And all of these nodes are airports in the worldwide air transportation network. And what is shown here is, using this effective distance, you can see what other places are effectively closed with respect to this perspective in Conakry, and what are the most likely spreading pathways throughout the entire network. And you see immediately that Charles de Gaulle here is a super hub in terms of the spread of risk of Ebola. In fact, there's also a model underneath that allows to try to compute these import risks. So what does that mean? Let's assume there are 100 people that are Ebola infected and asymptomatic, so it's not noticed. Let's assume 100 leave this airport right here. The underlying model would say that 4 of those people would end up in Charles de Gaulle. You can also click on, say, Germany. You'll see there are all the German airports, and what you see immediately that they're a little further away than, for instance, Charles de Gaulle or Dubai. And what you can also do is, and that's insightful, I think, when you change the reference point to Freetown in Sierra Leone, which is just a neighboring country that is also affected. So this is the one big airport in Sierra Leone. And you can see that here the most important spreading hubs are London Heathrow, the London Gatwick, there's Charles de Gaulle. You can see immediately you just change the sort of the location, and then other airports become important in terms of disseminating the risk of import through the worldwide air transportation network. That's not so surprising because there's kind of a colonial footprint in the air transportation network. So Freetown or Sierra Leone, former British colony, and Guinea, former French colony, you can still see that these hubs that are European hubs that connect to these places still play a role. You can also, change this again. Here's Monrovia in Liberia, and you'll see that Brussels plays a. I think here we go. Dubai is reached through Accra, and for every of these nodes, you can use the model and compute the import risk, etc., using this sort of method without having to dynamically model a disease. Okay, you can also check what happens. That was in the media quite a bit. Let's look at the perspective of the spread of risk from Conakry. You may think, well, maybe this link is very important because everything is going through Charles de Gaulle and reaching the rest of the world. Maybe it's a good idea to cut this link. So let's do that and see what happens. And you can see that even though this link no longer plays a role, everything kind of reorganizes, and it turns out that this sort of potential containment is very ineffective. It's not only very ineffective, it also makes the whole system more unpredictable. There was in the media a lot of discussion about, containment by, travel restrictions, and it turns out, and that is consistent with what other people have found, it actually makes the system less predictable, more problematic, because everything just kind of redistributes maybe through airports that you don't want to have playing a key role in your system. So with that, let me go back here. I'd like to thank you for your attention, and looking forward to your questions.
Very much for this very interesting talk. We have time for questions now. Yes.
Thank you for a very interesting talk. You just mentioned airport restrictions, and I was also wondering if you could include them into the model. Like, for example, I know in Asia a lot of people are scanned via infrared according to their body temperature, and then they are not allowed to enter the plane. I mean, these data are kind of available, so could you not just include them into the model?
Oh, we do. This is just a glimpse of the system. And just to illustrate that with the system, you can immediately see what kind of effect containment measures would have. What I showed you were travel restrictions, just, knocking out links. But you can also take nodes and put a filter there and say, okay, by putting containment measures at an airport, you reduce whatever you have as a probability of going to the airports that follow in the chain. So that sort of thing is actually in the tool itself, not in the online version, but the one that is used by the people, for instance, at the Robert Koch Institute who do like this kind of policy development.
Thank you.
Thank you very much. Maybe I understood you wrong, but I think you just look now. Your point is that you want to switch focus from the geographical distances to the kind of distance by air travel, which would result that Berlin Airport would be a good place to quarantine Ebola
Absolutely, yes.
patients. I mean, wouldn't be a better compromise to mix both distances? I mean, people travel from, especially from Pittsburgh to New York by other ways.
Yes. So, sure. The best way to, or the next step in this sort of analysis, if you want to address questions on every length scale, you would have to look at networks that contain more means of transportation. We have done this in other things. In other settings, the basic take-home message here is, this sort of thing is for addressing questions on a global scale. If you look at if you want to address something like this, like we did for Germany, for food transportation, it's a totally different scale. At the end of the day, the whole method is you have a network, and then you look at this effective distance that is imposed by this network. And it doesn't matter whether it's air traffic or trains or anything together. The whole idea is that a spatially embedded network can be used to redraw the geography. And to me personally, this was important because there's a lot of opinion in the community that these network spreading phenomena look complicated, hence they have to be complicated. And I think that is to some extent also misleading. Sometimes there's just a simple pattern hidden in these processes. We have Alex Vespignani, who I mentioned earlier. He and his student have now analyzed the spread of memes on Twitter networks using this, and apparently from what I see, it also works very well. So it's really that it's a way of looking at networks. It's a combination of, you are a node in the network, what's your perspective, and then having some sort of better notion of distance. The other aspect of this is, and I forgot to mention it, is that I'm also partially, I partially work at the Robert Koch Institute, which is the public health institute in Germany, and I can assure you that policymakers, especially those that deal with security issues, they still think in a very old-fashioned way about the world. They think about national boundaries, regions, geographic distance, regional containment, etc. So I think that's another message of this, is that we just need to think about the system in a very different way, and there are so many other systems that kind of point into that direction. It was a very long answer to your very specific question.
Yeah, thank you. Is this working? Okay, so now it is. You basically just answered my first question, which was in food chains, supply chains, for example. This is so unpredictable sometimes where it actually goes. But obviously, you can also deal with that in the model somehow. And the second question was actually, how does the nature of, for example, the disease play into this? Like if it's airborne, or if it's food, or if the incubation time is very short or very long, how does it change the friction of the traffic?
So, one initial point about all of this, why we started this, is we had computer simulations that incorporated all sorts of parameters about traffic, parameters about the disease, incubation periods, infection times, recovery rates, age structure, all of these things. And to me, it was clear that if you put it all together, you get a picture, and it's fairly consistent to some extent with what you will observe. But it seemed like different sets of parameters shaped different aspects of the spreading phenomenon. So, for instance, these waves that spread in this effective distance concentrically always have this shape within reason. But the speed, for instance, is governed by epidemic or disease-specific parameters. And it was very important to me to kind of segregate the parameters and identify these parameters influence this aspect, these parameters influence that aspect. And just to answer the question, is it at all possible to have this kind of segregation of parameters? So to some extent, what we have done here for Ebola, I can just, plug in the MERS coronavirus, which is a totally different virus, or chikungunya, which spreads in a different way. But this is all about traffic. It's all about mobility. It really factorizes out the epidemic-specific parameters within ranges. So there's some sort of broad assumptions that you have to make about that.
Here.
Oh.
Yes. What could you say about the non-human contagion disease like the chikungunya that you have?
Yeah, that's a vector-borne disease. So, again, that is an event that started in the Caribbean, and I wish I had a similar page for you like this. There is one on the web page. We haven't gone online yet, though. That's a disease where the spreading is different, okay? Nevertheless, there's a location where it started, like the Caribbean, and there are cases now in other places like the US, I think. And again, we can get a good notion about how this spreads by looking at human mobility, because humans that are infected, they go from A to B, and potentially a new vector takes the disease and spreads it in the local place. So the coupling between places like the Caribbean and Mexico, the Caribbean and the United States still plays a role. So if you think about the traffic of individuals, not as much as it's just individuals traveling, but it's a proxy for a coupling strength between places. If you take it up in a level of abstraction, if you think about coupling strengths like in physics, then you can still use this sort of thing, because the mechanism, the transmission, that's a disease-specific mechanism, but nevertheless, you can get an idea of how this spreads geographically by just looking at the coupling between places. Okay, so the disease transmission is factored out of this picture. Okay, in fact, even if you do something like this for countries, you look at the mobility networks between countries, and you look at something like the exchange of goods or a trade network, you get not exactly the same kind of networks, but you get very similar networks. In fact, if you look at, say, the World Air Transportation Network from the perspective of Germany, and you look at the World Trade Network from the perspective of Germany, they don't look so much different. So it's really the coupling strength that is driving this sort of thing. Yes, a very good question. Mm-hmm.
Effectively, it could be from anywhere.
Yes, that's a very good question. So that sort of thing can happen. So when you start, for instance, removing a little bit of data, or like adding some sort of noise on data, because in the perfectly simulated epidemic, you know everything, but not in the real world. So let's assume we're adding a little noise on everything, on the network that we're using, on the sort of cases, etc. Then you no longer get points, you get point clouds. And they have an overlap. And so you get kind of a probability distribution. How likely is this guy going to be my outbreak location? And then you can indeed have situations where you have a group of potential outbreak locations, but they're not necessarily geographically close. Okay? So yeah, and you get also other things when you have like multiple outbreaks. But that's a very good point.
Okay, let's thank the speaker once again.
Thank you.